Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 4. Student, this is lecture number 4, and basically in this lecture we will start the remaining example of MC cormic working. Lecture number 3, basically what we covered, we basically covered all these examples, which is around about 20 examples, and the design of simply supported beam and a cantilever beam. Okay, here we have basically starts from example number problem number 4.212, and we will end these examples. Okay, so here we will basically see the design of overhang beam with pattern loading. This is very important. You will understand what basically means pattern loading, and the design of non-rectangular beam. This is also a very important topic. Although we basically design a rectangle beam, but if you face any kind of a non-rectangular beam, so how you can design that. Okay, similarly you see 1-2 examples on one-way slab design, and similarly you see how we can design a stem of a retaining wall. Okay, so this is very important lecture. Here we have basically the design aids. We covered this section from SAM design aids, and I already explained this in lecture number 3 that how to use these design aids. So all those students who joined me the first time, so I will just suggest him to please watch lecture number 3 and then watch this lecture. Okay, because if you don't watch lecture number 3, you couldn't understand, because all the things I explained in lecture number 3, I am not able to explain all those things here because it will take time. Okay, and it will lengthen my time. Okay, so basically I always try to concise the thing, to shorten the things. Okay, so let's start. The first example is this non-rectangular beam example. What we have in this example, select reinforcement bars for the beam shown if mu is equal to 25 to 250 feet cube, and this is Fy, this is Fc prime. Hence is given, assume that the distance from the center of gravity of the tensile steel to the center of gravity of the compression blocks equals to 0.9 times of the effective depth. This is assumption. This is here we are allowed that you can use this assumption. After a steel area is computed, check the assumed distance and revise the steel area if necessary. Okay, here we have to check whether our steel is yielding, mean that we are in tension control zone, or our section is compression control zone. So here you, inshallah, you will see how we can use this epsilon t. Okay, so let's start. Okay, first of all, we will using that assumption 0.9 it is given, and the effective depth which is assumed, which I am using here, is 24 feet. D is equal to 24 inches. Sorry. So I have to multiply that 0.9. It is already given, okay, to me, and 21.6 inches is now my Z. That is the distance. Okay, it should be clear here that hence is given, assume that the distance from the center of the tensile steel to the center gravity of compression block. If I show you this assumption, let me show you here. For example, if you have a rectangular beam or any kind of beam, so you all know that we have a tension force, okay, and we have a compression block, concrete compression block. Okay, so concrete compression block like in rectangle shape. Clear? So we have C force, that is C central compression force, and we have a tensile force. So the distance, that is the lever arm. So here it says that you can use this lever arm equals to 0.9 times RD. Clear? So this distance is basically nothing, it is that lever arm. Okay, so on the basis of that lever arm, we calculate AS mu divided by 5 Fy into Z. Z is basically lever arm, that is D minus A over 2. Already we know it. So using the same equation, just plugging the Z value, and we got the area of steel 2.572 inch square. Now we will calculate the area of concrete compression block. Okay, you already know that this is the concrete compression block, and how much its area. This area is basically known as AC. This frontal area of concrete is basically known as AC. And you already know that this area is equal to what? This depth is the concrete block depth, that is A, and its width is basically taken as B, that is 12 inches, or you can say this is B. So AC is basically nothing, this is equals to BA. Clear? So this is concrete block frontal area. Clear? So here basically we calculate that AC, and you already know that AS or MU, you already know this. This is the concrete block formula, and this is basically if you compare T tension force with compression force, so you can got that T is equal to AS Fy equals to C force is nothing, that is 0.85 FC prime into BA. So we just replace that B by AC. Okay? So from AC is leaving here and this term is shipped here. Okay. So this is the basic mechanism behind this formula. We got 45.38 inch square. Now the tricky part of this question which need to be understand is noting here that we have a compression block, okay, and then the section is non-rectangular. So this is a non-rectangular section. So we have to find out this area. This is area of compression. Okay, here tension and here is compression. So our neutral axis is around about here. Okay, so this is our neutral axis. We have to find this location, that is y bar, the location of the neutral axis. Okay, this is my neutral axis. Now remember, this area is can be determined by multiply 5 with the 6, so we got 30 square inches. Now the area AC which we calculate, that is 45.38 inch square. So this means that the compression area is more than 30 inch square. It suggests that this basically suggests that that the neutral axis lies within this larger rectangle. Means like in a T-beam analysis, we basically check that whether the neutral axis lies within the flange or within the web. So here you can say neutral axis lies within the web. You can assume this. Okay. So now here basically my concrete block thickness will be this much. Okay, this much is my concrete block thickness. So already I know about this 6 inches, but I need to determine this distance. Okay. So how I can determine this distance? I need to find out this area. This area can be found out by AC minus this area. And if you do this calculation, AC minus that AC, that is 45.38 minus this 30. So you got 15.38. So this area is nothing. This area is now 15.38. Okay, 15.38. Now if you divide this area by this longer sides, you got this side, and this is 1.03. If you divide 15.38 by this length, that is 15 inches, so you got 1.03. So here you see basically 15.38 divided by 15, so you got 1.03. Now our A is now 6 plus 1 point. This is our A. Okay, I already show you that this is the concrete block, and the thickness or the depth of that concrete block is A. And A is what? 6 plus this distance, that is 1.03. I think so this is clear. And now once you calculate your A, you have to find out your y bar, that is the location of neutral axis. It is nothing, you just need to find the moment. You just need to find the moment about this plane, the top of the plane, okay, of the section. Now the area, that is 30 times the moment of this area, that is 6 divided by 2, that is 3. So 30 times 3 plus the area of this moment, the moment of this area, so that is 15.38 area, and we have to multiply this with the centroidal distance, that is 6 plus 1.03 divided by 3 and divide by the whole area. Okay, so this is just only you can say the same procedure as you will adopt it for finding the neutral, the centroidal axis. Okay, so you already know this technique. That let me write down the formula. AY bar equals to A1 Y bar Y1 plus A2 Y2. So this is the formula. Now you see that did the calculation dividing by the whole area here. Sorry, here we have divided by the whole area, we got 4.19 inch. This means that the location of Y bar is 4.19 inch. Now again we have to calculate our Z, because we have to verify this value. Okay, this value whether it is okay or not okay. So that why, because 4.19, so again when I repeat my lever arm, so I got 19.81, and 19.81 is not equals to 21.6. So that why I am using again trial 2. This is basically trial 2, trial number 2. Clear? So I again recalculate AS, I got 2.804 this time. Again I recalculate AC, and this time I got 49.49. And once again I calculate Y bar, so it will give me 4.437. And when once I again I calculate lever arm, so that is 19.56. So now you see 19.81 and 19.56 is close. You can use again trial 3. On trial 3 you got a very close value. So here I am stop my trials and I just say that this is close to this one, this value. Both the values are close. So I stop my trials, and this is now my final AS. So this is my final AS. Okay, now we have to provide now bars for this area. Clear? And recalculating my A value, now my A value is again 6 plus 1.3 is nothing. It is basically found out from this 49.49. So you just need to subtract 30 from this value, 30 from this value, and the value which you got, divide that value, that is, you can see 19.49. 49.49 minus 30, you got 19.49, and divide that value by 15, you got 1.3. So this is my final A. Okay, this is my final A. And to check the, basically to check the strain value, that is epsilon T value. So epsilon T value, I write down this formula here. You can see what value I needed. I needed the effective depth, which I already determined. Now I need C. So if you want the value of C, C is nothing. This is equals to A divided by beta 1. Clear? So I know about beta and I already calculated A. So I got C value. Okay. So this is the procedure why I am using, or why am I calculating C value. So my A is determined. I know about the beta 1 value. So my C value is now at 159. And from those values I got epsilon T, and you see epsilon T is more than that value. So this value basically suggests that your tension, your section is under tension. It is a tension control section. If it is less than this value, so that will suggest that your section is not a tension section. And this also suggests me that you can use to determine your capacity of your section and the capacity of your section by using 0.9. Clear? So this allow me, if this value is not greater than this value, so I have to recalculate phi value, and from which equation? From this equation. Remember this equation. I have to insert all these values, epsilon y, epsilon t, which I calculated, and epsilon y is what, 60 divided by 29,000, and that value which I got from phi, which is less than 0.9. Remember, I will use that value then. Okay. So this is the basically concept behind that, those formulas. Okay, and remember this value should be more than this one. Okay, otherwise you have to recalculate your phi value and you can't use this 0.9. Clear? So this ends up my question number 4.121. Now question number 4.22. Now if we see question number problem number 4.22, repeat problem, same problem for 150 feet. So this question is simple. Okay, you see the same question, just only the moment is reduced. So if you see moment is reduced, what it basically produces, you see this is 27.23 now. AC is 23, which is less than 30. So that suggests that your neutral axis lies in the first block, not in the second block. Your neutral axis now here. Okay, this is basically the key purpose of this example, that you will understand. You can say the neutral axis lies within the flange. Okay, neutral axis lies within the flange area. In the first question, with neutral axis lies here, but here in this question, neutral axis lies in the first zone. And the same calculation, the same trials, and they got A is equal to 1.57. Okay, 2 number at bar will sufficient for this area, and again they use C epsilon T, and again you see epsilon T is more than this one. So that means you are eligible to use phi value equals to 0.9. Okay, so here you are 0.00 add 0. It is more than the first example as well. Okay, the next example is 4.23, and in example number 4.23, here we have two examples. Okay, design rectangular section for the beams and loads shown. Beam weights are not included. We have to include the beam weight. We have to assume it 300, 400, whatever. And Fy is this much, Fc prime is this much. Live loads are to be placed where they will cause the most severe conditions. This is how we call pattern loading. Okay, and I think so most of the students did not know about this. Okay, so you see here how we can shuffle basically the live loads and how we can determine the maximum moments, positive and negative. Select beam size for the largest moment, and then select the steel required for maximum positive and negative moment. Finally sketch the beam and show approximate bar locations. So we have this example and we have this example. Okay, and remember rho value is given. Clear? The rho value here is 0.5 times of rho b, and here the rho value is 0.1 Fc prime by Fy. So let's start. Assume the bare weight of the beam as we did in lecture number 3. Okay, calculate W dead, W live. This is my dead ultimate, this is my dead live. So this is the pattern loading. Remember, for positive movement you have to place the live load in the within the between two supports. Okay, while for maximum negative movement you have to place live load here, like you see here. You can also do the same calculation by placing the live load on the whole section. Okay, it will give you you can compare those negative movements and positive movements with these movements. If it is more than this one, so you can use those one. But remember, when you have cantilever, singly cantilever beam, overhang beam, the maximum positive movement you can got for this load pattern when your live load acting here, and the maximum negative movement will be when your live load is on the overhang portion. So this is basically the key concept behind pattern loading. This is how we call pattern loading. Okay, so once we place live load here, we got maximum positive movement is 317. Here you see, here we have 3.2 foot cap. This is minimum positive movement. Here we see the negative movement is minus 11.8, and here you see the maximum negative movement. So we will design for this negative movement and for this positive movement, and we ignore these values. Okay, so select beam size on the basis of rho. So rho value is given 0.0120. Go to the table A13, I think so, and find out this value. Remember, if you don't have that table A13, so you can this value is basically from where? From this design aid. I already explained this in lecture number 3. So you can go to the lecture number 3 and you can choose there. You can learn how to use this. Okay. So this is 4,000 and 60,000 steel we have. Okay. So rho value, this is my 60,000 and 3,000. I have this table. Okay. So here what value I got? Basically 0.012. So 0.012 basically where it is, this is 3000, and 0. This is my rho value. These are my use. Okay. So where is 0.012? Okay, I could not find here because I have basically here I can search it 0.102 here, this one, no, this one, okay, this one. So my R value, this is my R value. Remember, if you don't have this table, you can calculate this 643.5 from a formula as well. We have a formula. Let me show you that formula. So this is the formula. Remember, we can get 643 from this formula. Just plugging the row 0.012 FY60 and same values here. You got that 643. Okay. So if you don't have that table, you can use this formula. You will got that value. Okay, this 643. So you can use either table, either you can use those formula. So from this, you have to find out your MU value, the same value. Now we are basically for a positive movement. So for positive movement, BD square equals to this one. Now we have to choose the section. I already explained this in lecture number 3, so please watch. And the final section is this one. And now we recalculate the beam weight. So rather this is high, but we accept it. Okay, you can recalculate and revise the calculation by increasing your beam weight, but this is okay. Already it is greater, but it is okay. Now we are designing for a negative steel and for positive steel. So our negative, this is basically our positive steel. I think so. This is our positive 371. This is negative. Sorry. So our negative, we are designing for negative movement. So you see our this is our R value. Okay, this is our R value. Now on the basis of our R value, this is our R value. Remember, here we are basically designing the question, not be finding just the R value. So plugging the R value, this one in the table here. Okay, not this table. Table A13. Okay, table A13. So here search that R value clear here this value, okay, in this, and you will find the row value. Now, okay, the things are reversed here. 633.94, 633. So where is 633 now? Here you see 643, 629, 634, which this one is close. Okay. Now you have to interpolate the value in between 629 and 634. You will use the interpolation technique and you got the value in between these two. Okay. So what that is basically 0.01188. So they basically select the value on the basis of this one, 634. Because you see 633 is close to 634. So because that's why they are choosing this one. Already you can interpolate or already you can select the larger one. Okay, code allowed you. Now I select 0.0118 from appendix and I got the area of steel this much. Now I'm suggesting 3 number 10 bars, and for positive again I use the same procedure 542. So here we have 542, 532, 542, 0.0099. Okay, let me check it. You see, I again recalculate and this is my number of bar. Now you have to place the bar, you have to show the section. Remember, if you are placing your bar, remember this is my critical section where I have maximum negative movement. So first of all, you must make sure that this bar should be extended for a distance of LD development length, and this bar must be extended for a distance of LD. Okay, similarly here this is my critical section, so this bar must be extended for a distance of LD and this bar must be extended for a distance of LD. Although we can place this this bar should be extended for a distance of L by 3, but if you are interested to find this LD from tables, so this is number 10 bar, and let me check it, this one. Remember this table is available in MC Cormic, Nelson and McGregor book. This is the formula and these are the tables. Okay, so that bar is basically my top bar. So for top bar, basically you see here, this is my FY 60,000 psi uncoated bar, remember, and this is 3 to 18, 3 to 6 inch dia bar, and 7 to 18 number. This is number of bar. Now I have to use basically this one, this table, and here right I have this one. Okay, so 61.7. okay, 61.7. now uncoated bars, normal wet concrete, yeah, uncoated normal wet concrete, yes, and other cases, yes, we can use this one, 61.7. okay, this one, and uncoated bars, normal wet concrete. But remember, there are basically, these are other cases. These two basically used for case 1 and case 2. So case 1 and case 2 is this basically explain that the distance between the bar, or the spacing between the bar in transverse direction, basically it must be greater than dB, and edge distance, this must be greater than dB. Okay, so if you are interested to know about these cases, you go to my playlist, my channel playlist, and find out the videos which is regarding to development length. So I already recorded 18 lectures on this, on these cases, on these cases, and I already show this table as well on various examples I have solved. Okay, so please go to my channels, and in my playlist I have uploaded those videos. Okay, so 61.7 is my but remember, you have to multiply 61.7 with the diameter of the bar, and my diameter of the bar is 1.27, that is number 10. So if you multiply them, you got round about 5 to 6 feet distance. So you have to place, you have to extend this bar for a distance of 5 to 6 feet, okay, to this left side. Clear? Similarly, the same question is here, which is W overhang, and this is the maximum negative moment, and this is the maximum positive moment. Okay, so the positive moment pattern loading you see here, when the live load is basically in between the supports, and the negative moment is basically resulting from when the whole beam is loaded with the total ultimate load, that is 5.16. okay, so and here the rho value is given, that is 0.50% of the rho B. And from where you got rho B value, I already explained this in lecture number 3, so please watch that lecture number 3. You got how to calculate the rho B, and this is calculated from, I think so, table A5. Now and already I explained the formula for this. So once you got your rho value, you find your R value, this from table A13, and then find out your BD. Okay, select the section and recalculate your beam weight. So we are okay here, and for positive and for negative you design the section, and finally you have to place the bars. Okay, so here you see the top bars are provided in the whole section, because if you check those LD criteria, so that's why basically LD is 6 feet and LD is 6 feet, so that's why they continue the bar in the top portion. Okay, so this is the reason, and this is question number, I think so, this is sample. Okay, here they basically design for negative, and here they basically design for positive. Okay, and they select just R value, and this on the basis of that R value they calculate BD, and this give you the choice of these sections, and the D which is decided is 17.5. Okay, so this is sample. Now the next question is 4.25. okay, so let me show you question 4.25. so question 4.25 and 4.26 is same. Design interior one-way slabs. So we have one-way slabs, the loads concrete weight is given, Fy is given, Fc prime is given. Do not use the ACI code minimum thickness, or you can say L by 20, L by 8, those coefficients are not allowed here. Steel percentage are given in the figures. The only dead load is the weight of the slab. So you have to just use the dead load which is equal to the slab weight. Clear? And no other ACI limitations that L by 20 or L by 21 or L by 28, whichever. Okay, here we have a simply supported one-way slab whose length is 24 feet. Remember, 24 feet is very, you can say, high amount of span length. And similarly on the other you see 16 feet, and you will see the placing the bar spacing for this. So you will see the spacing in this example, okay, because the dia of the bar in this slab and spacing. and similarly here it will be less because the span is less, but the loading live load is here, you can see 150, and here you can see 100 psi. So let's start this example. Okay, here we have, okay, assume basically assuming the slab thickness that is 7.5 and effective depth is 6.25. Clear? Dead load is calculated, that is the self weight of the slab, and WU, that is the total factor load, and MU is calculated. Now rho is already given, that is 50% of the balance steel ratio, and balance steel ratio is taken from table F5 of MC Cormic book. Clear? So I already explained this, how to select this in lecture number 3. Okay, so please watch lecture number 3. Now the final reinforcement, this is not the final reinforcement, we have to recheck. Okay, so this is now is our rho value. Now on the basis of this on the basis of this value, we select this R value from table A13. Now from this R value we recalculate our effective depth, that is 6.14, and already we have on the safe side. So that's why this is our now our final 6.25 is more than 6.14. So that's why it suggests that our assumed slab thickness is okay. Okay, because it is the limitation of the question that you have to use L by 16 or L by 18. Okay, we are not allowed here to use those deflection control checks. We have to select the depth, or you can say the slab thickness from this check. Okay, so this is the way that how you can assume the slab thickness without using these coefficients. So once you use we check the depth, so our final depth is this one is okay, and now we recalculate this value mu 5bd square. So we know about mu, that is this one. Okay, this one 25.38, which is converted to basically pound feet and pound inches. Then again it is multiplied by 12 to convert it into inches, with 1000 to convert it into pound, and similarly B is 12 inches and D is 6.25. we got this is the R value. Now on the basis of this value we have to choose rho value. So go to table A13, find out this value, and then once you got this value you have to find this value. Okay, so I already explained the procedure in example number 4.22, I think so. So once you got this one, you have to find out your A is and select the number of bars. So you see number 8, the rate of 9 in center to center. This is how, which I already mentioned, that 24 feet is the span of your supported beam, one-way slab. So that's why number 8 at the rate of 9 inches is a very huge reinforcement in your slab. And shrinking reinforcement, that is the 0.0018 times of BD, and this is number 3 at the rate of 8 in center to center. Okay, this is example number 4.26. You have to do this by your own, and this is a simple example. Okay, the same procedure is followed here. And example number 4.27, let me show you example number 4.2. Repeat problem 4.25 using ACI codes minimum thickness requirement for cases where deflections are not computed. Do not use the rho given in problem 4.2. Okay, you are not allowed here to use this rho value. And repeat problem 4.25 using the ACI codes minimum thickness requirements for cases where deflections are not computed. Okay, so let's start this example. We are allowed here to use those deflection coefficients. Okay, so what we have, this is minimum T, already this table is given, okay, in MC Cormic book, and I already explained. This is my so many videos. If you watch my channel you can find these values. Okay, and I already included this table as well in these design aids. Here I have this one. Okay, so here you see solid one-way slabs L by 20 when you simply supported slab. Okay, so L by 20 14.4 inch from ACI, and this is basically a slab repeat problem 4.28. okay, deflection are computed, do not use this one. Okay, Now you see the slab thickness, that is 14.4 inches from ACI. Assume 14.5 inch thick slab. Effective depth is this much based on 3 by 4 inch cover. Weight of the slab is this one. W is calculated and MU is again 32.94 feet kept. Okay, this is very huge moment in slab basically. So you will calculate this factor, that is 208.5. Go to table A13, find out this row value from table A13. Okay, and then your row minimum is larger of 0.0033 are again the row minimum formulas. I already explained this in here in design aids where I have this one. Okay, I already write down these equations. Clear? So in lecture number 3 I'll explain it. Okay, and my row minimum is 0.0033 and remember this value is more than this one, so that's why our this value is okay. Okay, and here I have being 0.572 inch square per feet. So number 6 at the rate of 9 inches sufficient and shrinkage reinforcement. Clear? So already the thickness is more, the reinforcement is reduced. This is the, you can say, the advantage of higher, you can say, higher depth of the or thickness of the slab. Okay, it will reduce the reinforcement. Okay, spacing, because number 8 at the rate of 9 inch, but here number 6 at the rate of 9 inch. Okay, and the span is again, span is same, material property is same, but here you see the deflection check. Okay, because if you are fixing your thickness of your beam, your slab, you have to basically check your deflection criteria, you have to check your shear criteria, you have to check your row minimum and row maximum. Okay, so next question is basically the same question, I think so. Using FC frame 3000 and 60,000 and row corresponding to epsilon t, this one, determine the depth required for a simply beam to support itself for a 200 feet simple span. This is very interesting. Okay, this question is very interesting. You have to find out the row value which is corresponding to 0.005. So let's see. This is example number 4.25. So the beam weight is assumed here and the base is BD divided by 144 into 1 times 150. So here we have this one. Okay, BD is still we don't know. Using ACI load factor equation, this is that one, WU 1.4, and okay, this is the pound per feet weight. MU is calculated in terms of BD, feet pounds. Okay, row value is 0.0136. Now remember, this is from table A7. Let me show you table A7. Already I explained it in lecture number 3. Here I have 3000 concrete, and here I have basically 4000, I think so. Let me check it my steel, that is 60,000. So 60,000 steel, this one, and here I have 0.005 strand. This is the row value. Okay, this is the row value 0.01. Okay, so I have to use this one. And MU by BD square, so go to table A13 or A12, A12 and find out this value R, this R value versus this row value. Okay, so you find this 685 versus this one. So here from here you will got your BD. Okay, so assume your B, okay, and calculate your D value. This is 141.9 inches, 11.83 feet. So this is the beauty of such kind of examples which make a kind of sense that, for example, if you are using 200 feet simple span, how much depth you needed? That is almost 12 feet. So you can say that the concrete beam span, basically when span is increasing from 30 feet or you can say 40 feet round about, of 3 feet depth of the effective depth of the beam is sufficient. But when this is increasing from beyond 40 feet, so you see you need a very heavy depth. Okay, you can say a 12 feet depth. So practically it is impossible. Okay, now the next example is I think so the same example. Okay, I think so the same example. And determine the depth required for a beam. Yes, supported itself only for 100 feet span. Neglect concrete cover and self-weight calculations. Cover in self-weight concrete. FC frame is 4060 ton. Now they more, a little bit increase the strength of concrete, and row values allowed 0.5 rupee. Okay, now we see what we have. Look it. Once we calculate mu, the same calculation. Row value is 0.01425 and mu is from table A13 we got this R value. Once I calculate, so here you see D is equal to 32 inches. Now this is practically possible. This is practically possible because the span is reduced, the material properties improved, and neglect beam weight below steel. This is very important. Below steel, basically that is the weight of your cover weight is neglected. BD basically. This is not total depth. This is D. Okay, effective depth. And this is the advantage. Okay, that once if you are reducing your span, okay, it will reduce your beam depth. Clear? Yes. Next question is 4.30, and this is a retaining wall stem. You have to design. Okay, this is your retaining wall, and you can say a load is a uniformly load is applied, and you already know the stress distribution in retaining wall will be in triangular shape, and 500 psi assumed lateral liquid pressure, and determine the step thickness. How much thickness is provided here? Okay, and maximum movement for the retaining wall shown in the accompanying illustration. Also determine the steel area required at the bottom and mid depth of the stem. If FC frame is this much, assume that number 8 bars are to be used and that in the stem thickness is constant. Okay, and the 18 feet height, also assume that the clear cover is 2 inches and row is also given. So all things are given. Okay, you just need to design as a rectangular cantilever beam. Okay, so if you know about the design of cantilever beam, you can do it. Mu is calculated. Mu is nothing, you can say the area 1.6, that is the factor. 1.2 tile, this is the area, and this is the half depth, you can say. Let me show here the area. What will be the moment here? Okay, what will be the moment here? So the moment will be the area of this section multiplied by the centroidal distance, and the centroidal distance 18 divided by 3. This is h by 3. So you already know this. Okay, how the triangular section area is calculated. Okay, so once you got your mu, you have to decide your row. This is given, and this is your row value. Now go to table A13, find out the R value, this one. Okay, and from this assuming your B value and find out your D. Okay, so the D value is 8 inches. Now this is the requirement of the question, that how much thickness. So we have to provide 8-inch thick retaining wall stem. Clear? The next part is use 11-inch thick wall. We are using 11 inch because the total thickness will be 11 inch, but the effective thickness will be 8.50. Now the steel area is calculated, and number 8 bars at the rate of 6.5 inch center to center. Okay, which will give you a steel area 1.45 inch square from table A6. Table A6 basically. So I think so I already explained this table A6. Yes, where is this table is? This table is I think so this one. This is table F5, but this table is available in McCormick book. Okay, so you can search this table in the last pages of the McCormick book and find out this table and find out this spacing. Okay, now they basically recalculate your row value. So row value is nothing, the area of steel divided by BD. So this is now you are providing row. Row minimum is 0.0033. So your row maximum is 0.0181. 18. Okay. So from this is from table F7. This one. This is from this table. Not this one. This table. Okay. Because from 40,000 steel, you can see here this one. Here. Your row B is basically row balance. This one, your epsilon T, this is your row max. This is the steel ratio versus 0.005. This is your rho max, and this is your rho provided. This is your rho value versus 0.0075. Okay. So your provided rho value within lies in which is more than less than this one and greater than this one. So you are okay. The section is under tension and it is a ductile section, you can say, and you are allowed to use 0.9. Clear? And the next question is 4.31. So this is all about precast concrete slabs. So we don't do this. I skip this. And this question also regarding to a flow chart. So I also skip these questions. And these are the questions which is regarding to SI units. Okay. So you have to do this by yourself. If somebody want to do these questions in SI units, already all those tables which you can see here, these tables are in SI units are available in MC Cormic book as well as in McGregor book. Okay, these tables are available, and these formulas which I discussed here are also available in MC Cormic book in SI units. So please go to McCormick book and find out those tables. This is the flow chart. This is the flow chart for a singly reinforced rectangular beam. Okay, you have to find it your MU, then FY, FC prime, and span length. These are the required data. You have to input this. You need to find out your rho minimum, because if you don't have those tables, you can do these calculations from these equations. Beta 1 is this one. Okay, but remember 0.85 when your FC prime is less than or equals to 4000. If your concrete strain is more than 4000, then you have to recalculate your beta 1 from this formula. Remember, this is for this condition. And beta 1 is 0.65 for FC prime greater than 8000 phase size. This is extra knowledge, extra information, okay, which I shared. User to specify rho. Then you have to specify your rho value, and then again you have to find your BD value. Okay, your phi will be 0.9. B should be assumed and D should be calculated. Remember. And we again for next try 7, 8 and so on, you can use different values of B and calculate your D values. Okay, until B is equals to D. Clear? And this is a flow chart. This is for 4.32. Do this by yourself. I think so. This is the continuous minimum service. User may specify a minimum H here if desired as per ACI code. Yes, H, he can use it. This is basically minimum thickness. Okay, and from deflection criteria, you have to find out that factor. Okay, and L by 8, L by 20, or L by 17, whatever the value will be. Okay, and you have to find out your S, decide your number of bars or spacing of bars, and recalculate your A value, then your C value, and check whether your section is under tension or under compression. Remember, you have to find out. This is another approach. I already explained this approach in lecture number 3. If your C over D ratio is less than this one, so your section is under tension, you don't need to go back. If this C by D is greater than 0.37, this means your section is not under tension. It may be in transition or it may be under compression. So you have to again modify your D value, increasing the D value, and then redo all the calculations and then check it. Okay, if this check is verified, then your design is complete. Until if this is not verified, you have to go back to your here and you have to revise things. Okay, so this ends up these examples, these questions. Okay, and please go to McCormick book. Okay, at the end you can see all these tables and SI units. The formulas are inside is given. Okay, and if you have any problems in SI units, you can comment and I will explain. And instead of this, if you have any question regarding these examples, okay, let me show you. This is the McCormick book, and I think yes, you see the formulas are given, okay, in SI units. Let me show you some formulas. This one, this is chapter number 4, I think so. So this is chapter number 4, and formulas in SI units. Let me show you here. The tables of the depths are given, okay, and where those formulas are in SI units, basically they give you all the formulas, okay. Let me check it, okay. Let me show you the formulas, miscellaneous equations in SI units. You see the formulas are given, okay, and this is for skin reinforcement, I think so, and SI units already they give you the formulas, okay. And one thing more, you must do these examples by yourself, okay, because if you understand these examples, so you will find easy to solve those examples. Remember, this is for the row value, okay. So the minimum percentage values are given, okay, and similarly here you see all the formulas are given in SI units. So this is basically that R value, okay, in SI units, and these are the various SI units, okay. And remember, the tables are given in the end of this book, okay. All the tables in SI units as well are available, okay. Let me show those tables, okay, where those tables are, okay, here. So these are the tables basically in US units, and these are the tables, okay. So these are the tables which I use, okay, a table A5, and here they are denoted. This is the table which we basically use it, and these are those tables, okay. And one thing more, okay, that is I think so table A6, I think we use it. So table A6, basically in one equation we use it. So this is table A6, okay. Basically in last question you see we use, if you are using number 6 bar, okay, and spacing, okay, so and you have a steel area, I think so we have an area of steel is 0.54, I think so, this one 0.54, I think so. An example number, we have an example, okay. Let me show you that example, this one, I think so, number 4, table A6, yes. So number 8, we are using number 8 bar at the rate of 6.5. So this is from table A6. So number 8, where it is, this one, this is number 8, and we are using 6.4, this one, clear? So let me show you 1.45, and the calculated reinforcement is 1.45, okay. So this is how we can select directly the spacing from by using these table A6. So this is the beauty, you can say, and the ease of using tables. If you command on these tables, so it basically makes your calculation easy, and you can be able to do the calculation in a quick manner, okay, by without using formulas, okay. And this ends up this examples, okay, these problems. If you have any questions, any suggestions, you need any kind of explanations regarding these examples, please comment it. I will explain these examples, okay. So I already uploaded so many videos which are available in my playlists, one-way slab analysis, beam designs, okay. So please watch those videos, because I can't explain in each video all the examples, okay. I explain all the things, okay. So if you watch those lectures, so you will be in position to do these calculations, remember. And one thing more, that I have already explained different other methods. This is a different method, but I already explained different methods, and coming lecture inshallah I will show you more other methods of ACI, okay, that you can use those methods as well to design these beams, clear. And in next lecture, that is lecture number 5, inshallah I will do some examples from chapter number 5, that is T-beam designs, and I think so W reinforced. I already uploaded examples W reinforced beam. This W reinforced beam analysis I already uploaded, Okay, you can search it on my channel. A very you can say very explanations. I already covered these examples, basically these examples, and available on my channel. And very basically I have recorded 5 to 6 videos. Okay, so please watch those videos. Okay, see you in next lecture. Thank you for